Okay. Hi Narmada. Okay, good evening. So let's wait couple of minutes for others to join, then we'll start. Yeah, let's wait few minutes for others, then we'll start. So in the meantime, any specific doubts or question from last class? Okay.
Good evening, sir.
Good evening. Hi. Okay, so let's start. Then in the meantime, others will join. So today also we'll be solving 3 questions from 2017 paper. Question number 2, 28 and 29. So am I properly audible to you?
Yes, sir.
Okay. Okay, so let me just share my screen and then okay, so is my screen visible?
Yes, sir.
Yeah. So this is question number 2 from 2017 paper, and the question says, for orthohydrogen the nuclear wave function and the rotational quantum number respectively are. So basically let's first understand some of the basics of what do we mean by orthohydrogen and parahydrogen, etc., and what do we mean by the nuclear wave function, rotational quantum number, etc. Then we'll answer this question. So this will be actually helpful for solving this type of questions. Okay, so basically okay, let me just check here. Okay, so basically hydrogen gas is basically two hydrogen atom connected by covalent bond, right? So this hydrogen atom has nuclear spin quantum number, which is represented by capital S. Nuclear spin wave function capital S is half for each hydrogen atom. So that means S is quantum number is half, means that's magnetic quantum number. That means the ms value, the possible values of ms can be minus half and plus half, right? That means the each hydrogen atom, the spin of each hydrogen atom has basically two types of orientation. One can be up spin and another one can be down spin. So for, let's say, for this hydrogen atom, the first atom, the orientation is up spin, and the second atom, for the second atom, the orientation is also up spin. So in this case, the spin of the two hydrogen atom are perfectly aligned parallel to each other, right? Parallel to each other, parallel spin actually. So this type of hydrogen, where having the two hydrogen atom having nuclear spin aligned parallel to each other, are called or named as orthohydrogen. or in para hydrogen, let's say this hydrogen atom, for this hydrogen atom the nuclear spin is down spin, and this hydrogen atom the nuclear spin is up spin. That means ms is minus up and ms is plus up, right? So for this type of hydrogen, the two spins are aligned anti-parallel to each other. So this hydrogen we call it para hydrogen. Now in ortho hydrogen you can see the two spins are parallel to each other, right? Aligned parallel to each other. That means if we parallel to each other means for this spin ms is plus up, and for this hydrogen atom the ms is also plus up, or it can be minus up. So the total spin quantum number of the hydrogen atom is 1. This is total spin quantum number of the hydrogen gas for ortho hydrogen case. So the possible values of ms is -1, 0, +1. So there is, for the ortho hydrogen case, there is 3 possible spin states. 3 possible spin states. One is -1, ms equal to -1, another one is 0, and another one is +1. So this is why having 3 possible spin states means we call it triplet state. Total spin quantum number 1. And also these two spins are parallel to each other. That means if we interchange these two spins, they are symmetric, right? They are symmetric. So let's just call it alpha 1. This spin, let's call it alpha 1, or this spin we call it, let's say alpha 2, right? So okay, so now so the two spins are parallel to each other. That means they are symmetric to each other. Now if we write down the three possible spin states, that means the triplet state, the wave function will be, just let's call it for hydrogen atom the possible spin state at alpha and beta. Alpha denotes the up spin and beta denotes the down spin. This is the spin wave function. And for another hydrogen atom, let's say this is H1, let's say this is H2, and another hydrogen atom, the possible spin wave function is also alpha and beta, right? This is denoting up spin and this is denoting down spin. For ortho hydrogen, the spin state is triplet state. That means 3 possible spin states having same energy. Now these 3 states will be, one is, let's say, H1 having spin alpha and H2 also having spin alpha. That means spin wave function is alpha 1 times alpha 2. Second state will be the H1 having spin beta, let's mean beta 1, and H2 having spin beta, that means beta 2. Now third state will be H1. This is a linear combination of linear superposition of 2 states. So the wave function will be 1 upon root 2, H1 having spin alpha, H2 having spin beta, plus H2 having spin alpha times H1 having spin beta. So this is a linear superposition of these 2 states. So these are 3 possible triplet states. Now if we see these states, if we interchange alpha and beta, hydrogen 1 or hydrogen 2. Now let's consider the case 1 first wave function. If you interchange 1 and 2 hydrogen atom, that means alpha 1 will be 2 and 2 will be 1. Interchanging means you are just interchanging the number of hydrogen atom, right? So 1 will be 2 and 2 will be 1. So if we after interchanging 1 and 2 hydrogen atom, the 1 will be this wave function will be transformed as alpha 1, replacing 1 with 2, alpha 2 times alpha 1, replacing 2 by 1, right? Now this is again, let's say this is 1 prime, so this is again same wave function, right? With this wave function and this wave function are same to each other, like similar, identical. That means after interchanging the 2 hydrogen atom, the total spin wave function corresponding to the triplet states of the ortho hydrogen gas are symmetric. Like if you interchange 2 hydrogen atoms, the wave functions will be identical after transforming it. So they are actually symmetric. So this is the story of ortho hydrogen. Now let's consider para hydrogen. Now for para hydrogen atom, the 2 spins are anti-parallel to each other. So the total spin quantum number S corresponding to this hydrogen gas, para hydrogen, will be 0. So ms, possible values of ms will be 0. So this will be the singlet state. That means spin multiplicity. How do you calculate spin multiplicity? 2 times total spin quantum number plus 1. That means 2 times 0 plus 1, that means 1. So para hydrogen has spin state singlet. That means only one possible spin state are there, singlet state. Now if we write down the wave function corresponding to the singlet state, it will be linear superposition of 2 states. In triplet state we considered the plus combination. So in singlet state we will consider the minus combination. That means hydrogen 1 having spin alpha, hydrogen 2 having spin beta, minus hydrogen 1 having spin beta times hydrogen 2 having spin alpha. So this is the wave function corresponding to the singlet state. Now if you interchange 1 and 2, what will happen? Let's interchange 1 and 2 in this case. 1 and 2 hydrogen atom. After interchanging 1 upon root 2, alpha replacing 1, it will be 2, then beta replacing 2, it will be 1, minus beta replacing 1, it will be 2, then replacing 2, it will be 1, right? Now just rearrange this 1 upon root 2. Okay. Yeah. Now if you rearrange this, so 1 upon root 2 minus of alpha 1 beta 2 minus alpha 2 times beta 1. Now let's compare these two, this wave function and this wave function. So these two wave functions are actually identical to each other, but with respect to a minus sign. So that means for para hydrogen case, if we interchange 2 hydrogen atoms, the wave function corresponding to the singlet state will be anti-symmetric. That means in this case the spin states are anti-symmetric with respect to interchange of 2 hydrogen atoms. Anti-symmetric. So actually we have answered the first question. So the nuclear wave function means spin wave function here. The nuclear wave function corresponding to the ortho hydrogen upon interchanging 2 hydrogen atoms. So we have seen that upon interchanging 2 hydrogen atoms, these three states are symmetric to each other, right? Are symmetric. So the nuclear wave function will be symmetric for orthohydrogen case. So the symmetric option is option B and option C. Now we have to find out the rotational quantum number for the orthohydrogen case. Now actually these H2 consists of two hydrogen atom with a covalent bond, and the spin corresponding to this hydrogen atom is +1. That means they will act as fermions. Why fermions? Because fermions are the particles having the half integer spin, and the bosons are the particles having full integer spin, like integer spins. So they will obey the Fermi-Dirac statistics, and the bosons will obey the Bose statistics. So they will act as fermions. So what do you mean by fermions? That means if you interchange these two hydrogen atom, the total wave function, that means if you interchange means if you apply permutation, like permutation operator, like interchange these two atoms, or if you apply permutation, the total wave function of this hydrogen atom has to be antisymmetric. That means because they are fermions, they will act as fermions. So that means they has to obey the Pauli exclusion principle, right? Pauli exclusion principle. And the Pauli exclusion principle says, now if you interchange two atoms, in this case two hydrogen atom in this case, or if you permute these two hydrogen atoms, the total wave function has to be antisymmetric to each other and has to be antisymmetric. This is the Pauli exclusion principle for the fermions, for the particles having the half integer spins, or fermions particle. Now we have seen that for orthohydrogen case, the nuclear wave function or the spin wave function is symmetric upon interchanging. Now interchange means you are rotating, right? You are achieving a particular rotational state. So the rotational wave function, or it is nuclear wave function is symmetric. Now the rotational state has to be antisymmetric in this case, because the total wave function has to be antisymmetric. So nuclear wave function for the orthohydrogen case is symmetric upon permutation or upon interchanging of two hydrogen atoms. Now the rotational state or the rotational wave function has to be antisymmetric to fulfill the Pauli exclusion principle condition, because the total wave function in this case is nuclear wave function times rotational wave function upon interchanging two hydrogen atoms. So nuclear wave function is symmetric for orthohydrogen case. Total wave function has to be antisymmetric to obey or to fulfill the Pauli exclusion principle condition. Now the rotational wave function has to be antisymmetric, right? Because symmetric times antisymmetric equal to antisymmetric, because plus times minus is minus. So it has to be antisymmetric. Now if you have to remember the rotational wave function here. Now if you rotational wave function we solve or we get by using the rigid rotor problem, right? Rigid rotor problem. Now the rigid rotor problem, the wave function or the solution of Schrodinger equations comes out as the spherical harmonics. Now for the property of spherical harmonics is very interesting. So for the spherical harmonics means the wave functions are spherical harmonics. Now the eigenvalue in this case for the particular rotational quantum number, let's say j, it will be j into j plus 1 h bar square divided by 2 times I, where I is the moment of inertia, that means m times r square. M is the mass and the r is the radius. J is the principal quantum number. Allowed values of J are 0, 1, 2, 3, etc. Now the property of spherical harmonic is for even quantum number, that means for j equal to 0, 2, 4, 6, etc. For even rotational quantum number, the rotational wave function or the spherical harmonics is symmetric or even function. Symmetric or even function. And for odd quantum number, that means 1, 3, 5, 7, etc., the spherical harmonics or rotational wave function are antisymmetric or odd function or odd function, right? So that means for orthohydrogen case, the nuclear wave function is symmetric. Now we have to find out the rotational wave function. The rotational wave function has to be antisymmetric in this case to fulfill the antisymmetric total wave function condition. So antisymmetric means the nuclear rotational quantum number will be odd in this case. That means j equal to 1, 3, 5, 7, like this. So to answer the question given, so the nuclear wave function for the orthohydrogen case is symmetric and the rotational quantum number will be odd quantum number. So the option B will be correct answer in this case. Now for orthohydrogen case, the option B will be correct answer. That means nuclear wave function is symmetric and the rotational quantum number is odd. Okay. So now another just fact. Now for parahydrogen case, the nuclear wave function is antisymmetric. We have seen that. So to fulfill the total antisymmetric condition of total wave function, the rotational quantum number, rotational wave function has to be symmetric. That means rotational quantum number has to be even quantum number for parahydrogen case. Now if you see the even quantum number means the rotational quantum number is starting with the value 0, and for the orthohydrogen case J is starting from value 1. So at low temperature, at very low temperature, the J equal to 0 is the possible state for parahydrogen, but J equal to 1 is the lowest possible state for orthohydrogen. So at very low temperature, the parahydrogen is more stable compared to orthohydrogen. Parahydrogen is more stable compared to orthohydrogen at low temperature. And at room temperature, the lots of states will be populated because of the high temperature or room temperature case. So at room temperature in hydrogen gas, the contribution of ortho and parahydrogen is 3:1. That means 3 orthohydrogen is to 1 parahydrogen. This is just for information. Okay, so any doubts or questions regarding this?
No, sir.
Okay, great. So let's move to the next question. So okay, so this is question number 28 from the same 2017 paper, and this is the question about the turnover number of an enzyme catalysis. So the question says, under physiological conditions, the conversion of carbon dioxide to bicarbonate ion by carbonic anhydrase enzyme, which the molecular weight is given 30,000 gram per mole, has a turnover number of 4 times 10 to the power 5 second inverse. Now the minimum amount of enzyme in microgram required to convert 0.44 gram of CO2 to bicarbonate ions in 100 seconds. So the turnover number is given here, which is the 4 times 10 to the power 5 second inverse. Also the molecular weight is also given 30,000 gram per mole, and we have to find out the minimum amount of enzyme required to convert 0.44 gram of carbon dioxide to bicarbonate ions in 100 seconds. Okay, let's first understand the turnover number, the definition of turnover number actually. So turnover number is basically the moles of number of moles of substrate converted into product per number of moles of substrate molecule converted into product by 1 mole of enzyme per unit time or per unit second. So the unit of turnover number is second inverse. That means per second the number of substrate molecules converted into product by an enzyme molecule. Here in the definition of this turnover number, it is assumed or it is approximated that the enzyme molecule has one activation state or activation state. Now on the one reactive state, that means. Now in this case the turnover number is 4 times 10 to the power 5 second inverse. That means the 1 mole of enzyme molecule actually converts the carbon dioxide, converts the 4 times 10 to the power 5 carbon dioxide mole of carbon dioxide to bicarbonate in 1 second. So 1 mole of enzyme molecule converts 4 times 10 to the power 5 mole of carbon dioxide to bicarbonate in 1 second, right? So in 1000 second, actually in 1000 second, the 1 mole of enzyme will produce like 4 times 10 to the power 5 times, sorry, in 100 second, in 100 mole of carbon dioxide to bicarbonate. Now we have to find out the minimum amount of enzyme required to convert 0.44 gram of carbon dioxide to bicarbonate in 100 seconds. So in 100 seconds, 1 mole of enzyme converts 4 times 10 to the power 7 mole of carbon dioxide. Now we have to find 0.44 gram of carbon dioxide, right? Now molecular weight of carbon dioxide is 44. So 0.44 gram means 0.44 divided by 44, that means 0.01 mole, right, of carbon dioxide. Now it is easy. So 4 times 10 to the power 7 mole of carbon dioxide converted into bicarbonate molecule by 1 mole of enzyme in 100 second. In 100 second. Now we have to find out 0.01 mole of carbon dioxide. what is the minimum amount of enzyme required. So 0.01 divided by 4 times 10 to the power 7, right? So it is 4 times 10 to the power 7, so 2.5 into 10 to the power minus 10 mole of enzyme required. Now we have to find them in microgram unit, so that means the molecular weight of enzyme is given, which is 30,000 gram per mole. So we have to just multiply this with 30,000. So multiply with 2.5 times 10 to the power 10 multiplied by 30,000. Which is 7.5 times 10 to the power minus 6 gram, right? Now the in microgram unit means 1 microgram equal to 10 to the power minus 6 gram. So the minimum amount of enzyme required is 7.5 microgram. 7.5 microgram. So the answer is 7.5 microgram. Okay, now this is actually one type of question regarding the turnover number. There can be multiple types of questions here. So basically the turnover number is the amount of substrate molecule converted into product by an enzyme molecule per unit time. Now in enzyme catalysis, or specifically in Michaelis-Menten catalysis, which is E plus S forming an activated complex, enzyme substrate complex, then transforming into product P. The rate constant is K1, here rate constant is K2, the backward rate constant is K minus 1. So in Michaelis-Menten, this is the Michaelis-Menten kinetics model corresponding to the Michaelis-Menten kinetics. Now the rate of transforming into product, that means dP dt equal to K2 times ES. Now if we solve this, it will be K2 times E0 times substrate concentration divided by Km plus S, right? So K2 times E0 is we call it Vmax, sorry, we call it Vmax times substrate concentration divided by Km plus S. Now we call it Km is the Michaelis constant, Km equal to K minus 1 plus K2 divided by K1, right? So Vmax, if we write down the Vmax equal to K2, or we call it K catalytic rate constant times E0, that means initial enzyme concentration. So K2 or K catalytic equal to Vmax divided by E0, right? Now this K2 or K catalytic, we call it turnover number. So in the question, if it is the Vmax is given and the initial concentration of the enzyme is also given, then we can also calculate the turnover number by computing the K catalytic turnover number. Now if you ask to plot the from the Michaelis-Menten kinetics, K overall divided against the substrate concentration, the plot will look like this. So this is actually Vmax, that means maximum possible rate, and at substrate concentration equal to Km, that means when Km equal to substrate concentration, the total overall rate will be Vmax divided by 2 half of Vmax. So this is half of Vmax, and this is Km equal to S. Now this is the plot corresponding to Michaelis-Menten kinetics, and there is also a Liner-Weaver-Burk plot here. So that means the overall rate constant equal to Vmax times S divided by Km plus S. Now if you this is called the double reciprocal plot, means if you just double inverse this, 1 upon k equal to Km plus S divided by Vmax times S. So 1 upon k equal to Km divided by Vmax times S plus 1 upon Vmax, right? Now if you plot this 1 upon k overall rate constant versus 1 upon S, double reciprocal means if you are plotting this with double inverse, like 1 upon k and 1 upon S, then you will get a straight line with intercept 1 upon Vmax and with slope Km divided by Vmax. Now from this slope and the intercept concept or intercept value, you can also calculate Km, like Michaelis constant, Vmax, maximum possible rate, etc. So this is the details of the enzyme kinetics. So the answer to this question is actually 7.5 microgram, minimum amount of enzyme required to convert 0.44 gram of carbon dioxide to bicarbonate ions in 100 seconds. So any doubts from this question? Otherwise we can move forward. All clear?
Yes, sir.
Okay, great. Just a second. So this is question number 19 from 2017 paper, and the question is about regarding the particle in a box problem. So basically the question says, assume 135 hexatriene to be a linear molecule, and the model, let's consider this molecule as a model, the pi electrons as particles in a one-dimensional box of length 0.70 nanometer. The wavelength corresponding to the transition from the ground state to the first excited state is, okay, so the molecule is given, this is 135 hexatriene. So let's first draw this. One, two, three, 4, 5, 6, right? So 135 hexatriene molecule. Now we are modeling this molecule. The pi electrons corresponding to this molecule are particles in a one-dimensional box of length 0.70 nanometer. So length of the box is 0.70 nanometer. So basically this is actually approximate model. So the 135 hexatriene is an actual molecule, and we are modeling the pi electrons as particles in a one-dimensional box. So basically pi electrons can resonate, like, so pi electrons can go from one end to another end, right? So that's why we are just modeling these pi electrons as particles in a one-dimensional box of length, a particular length 0.70 nanometer. Okay, so let's first draw this. This is the length of the box, and this is infinite potential. Inside the box V equal to 0, outside V equal to infinity, 0 to L, 0.70 nanometer. Okay, so you can understand we have to consider the particle in a box eigenvalue problem. Now if you solve the waveform Schrodinger equation corresponding to the particle in a box problem, you will get the eigenvalue expression En equal to n square h bar square, sorry, n square h square n square h square divided by 8m l square, right? Where n is the allowed quantum number. Now for particle in a box problem, the allowed quantum number is 1, 2, 3, etc. The n equal to 0 is not possible because of uncertainty principle. Okay, so h is the Planck constant, m is the mass of the electron mass, and l is the length of the box. Now for 135 hexatriene molecule, there are 3 pi bonds. That means there are 6 electrons are inside. If you just draw the energy level diagram corresponding to the this expression, so it will be n equal to 1, then n equal to 2, then equal to 3, n equal to 4, like this. So the energy gap between these two will increase with the increase of quantum number. So for particle in a box problem, this is a quite extra information. So particle in a box problem, the energy gap between the two energy states will increase with the increase of quantum number n. Actually it will increase with the quantum number n increases. So let's just fill out this energy level. So there are 6 electrons. So n equal to 1 state, there will be 2 electrons. N equal to 2 states, there will be another 2 electrons, and for n equal to 3 states, there will be another 2 electrons, right? So the 6 electrons are filled up in three states. So this is the ground state. This is the ground state corresponding to of the 135 hexatriene molecule. Now the first excited state will be the transition from n equal to 3 to n equal to 4. Transition of an electron from n equal to 3 to n equal to 4 state, right? So if you draw the energy level diagram corresponding to the first excited state of the molecule, so it will be n equal to 1, n equal to 2, n equal to 3, n equal to 4, right? So n equal to 1, there will be 2 electrons, n equal to 2, there will be another 2 electrons, and n equal to 3, there will be one electron, and n equal to 4, and there will be 1 electron. So this is the first excited state, first excited state of the hexatriene molecule. Now we have to find out the wavelength corresponding to this transition, ground state to first excited state. Okay, so we know the En equal to n square h square by 8m l square. So we have to find the difference of en plus 1 minus En, right? So it will be h square divided by 8m l square, n plus 1 square minus n square, right? So it will be 2n plus 1 h square by 8m l square. Now this is delta E in energy scale, energy dimension or energy unit. Now we have to find the wavelength. So we know the E equal to h nu or h c bar lambda. So let's just put this hc by lambda equal to 2n plus 1 h square by 8m l square. So 1 upon lambda equal to 2n plus 1 h square by 8m l square, and divided times 8c. So lambda will become to 8m l square times 8c divided by 2n plus 1 h square, right? So basically here transition is n to n plus 1. So in this case where transition is 3 to 4, so the value of n is 3 here. So lambda corresponding to this is equal to 8 ml square times 8c. 2n plus 1 means 2 times 3 plus 1, that is 7 times h square. So 8 m means 9.1, mass of the electron 10 to the power minus 31 kg. L square means 0.70 nanometer, that means in meter unit 0.7 times 10 to the power minus 9 meter square, times c. C means speed of the light, that means 3 times 10 to the power 8 meter per second divided by 1 h will cancel, so 7 times h Planck constant, 6.626 times 10 to the power minus 34, right? So if you just compute this, it will be just 231 nanometer approximately. So basically the wavelength in this question, it is asked the wavelength corresponding to the transition from the ground state of the molecule to first excited state of the molecule. So the ground state of the molecule looks like this, and the first excited state of the molecule looks like this. So the transition wavelength will be just lambda equal to 231 nanometer. Okay, so this is actually particle in a box problem, because this is linear molecule and we are modeling this molecule as a linear, and the pi electrons as particles in a one-dimensional box. But for closed molecules like benzene, naphthalene, anthracene, like this, these are resonating, these pi electrons are resonating, are participating in resonance. So we will model this closed molecule as particles in a ring, one-dimensional ring, particles in one-dimensional ring. So that means one-dimensional ring means just a closed circle here. So basically the radius of the circle is constant here, and the theta is changing, the angle will be changing. Now if you solve the Schrodinger equation corresponding to this, the energy eigenvalue will be, let's say E ml will be ml square h bar square divided by 2I. Just remember this, you will need this to solve another like similar questions. So here h bar equal to h upon 2 pi, that means h is the Planck constant and I is the moment of inertia, which is equal to m r square, right? Now ml is the quantum number. Now the possible values of ml or quantum number in the particle in a one-dimensional ring is 0, plus minus 1, plus minus 2, plus minus 3, like this. So in this case the 0 value is allowed. So now if you just put this for ml equal to 0, there will be just one state, right? Just one state, ml equal to 0. Now for other values of ml, like for ml equal to plus minus 1, for ml equal to plus minus 2, for ml equal to plus minus 3, etc., there will be two possible states of energy, right? For ml equal to, like, energy goes with ml square. So that means for particular value of ml, there will be two, ml equal to plus minus 1, there will be same energy state corresponding to two quantum state. So that means same energy state corresponding to ml equal to plus minus of 1, ml equal to plus minus of 2, right? That means for ml equal to 0, the energy state is non-degenerate. And for other values of ml, the energy states are doubly degenerate because two same energy states are possible, right? That means they are doubly degenerate. Similarly, you can just fill up the electrons here in the energy level diagram, and you can just compute the transition wavelength from this expression using this expression. And another extra thing is that the wave function corresponding to this particle in a ring problem is 1 upon root over of 2 pi exponential I ml phi. Now if you just operate the z component of angular momentum, that means minus a z m, you will get the eigenvalue corresponding to ml h bar. It is the z component of angular momentum. Which is the operator is basically minus I h bar del phi. So if you operate this phi ml, you will get ml times h bar phi ml. This is the eigenvalue, and the total angular momentum will be like L into L plus 1 h bar. This is total angular momentum. Okay, so in this question the total the wavelength transition wavelength is 231 nanometer. Okay, so any doubts?
No, sir.
Okay, then I think we'll meet in the next week. If you have any doubts from other topics or any specific topics, you can ask, or otherwise we'll meet in the next week.
Thank you, sir.
Okay, thanks for joining. Thanks. So we'll meet in the next week with another 4 or 5 questions and new topics. Okay, thanks. I'm signing off. Yeah, bye.